Hello and welcome to this discussion on the independent samples t-test. In this video I'll be going through the same exact sections, the data entry, descriptive statistics, null hypothesis and estimation, and sample size. And so let's go ahead and take a look at what that looks like for the independent samples t-test. So let's start out by thinking about the population. Remember, we start out with a population and then we draw a sample from that particular population. And in this case, because we have independent samples, we are going to draw two samples, and I'm going to call them N1 and N2. So we have two different subgroups within our sample. And when we measure them, then what that automatically means is that we will have an X bar for each of those different samples. And we'll also have a standard deviation for each of those different, oops, that's supposed to be a 2. We'll have a standard deviation for each of those different samples. And so here we've measured something, and because we have an X bar and a standard deviation, what that means is that we have measured something continuous. So that will come in handy to know later. And then, as always, we want to infer something back about the population, which is the mean and the standard deviation of the population parameter. Now, as you can probably imagine, instead of having just one mean, we're going to have two means that we're inferring something about the population, and two standard deviations that we're inferring back to. So let's take a look at what that looks like if we are to look at the data entry part of that. And remember, here's our golden rule of data entry, is that each row represents a person. So that represents a person, this represents a person, and so on. And so this person has a specific measurement, a continuous measurement. So here's whatever number represents that for person number 1. And then we also have to let the computer know which group they're in. And so this second variable here is a categorical variable, and that's what CAT stands for, CAT for categorical. And I've specified that this is a categorical variable that has two categories. So this is my kind of like sub-nomenclature here. We have a continuous variable that we have measured for each person, and we have also taken a note of exactly which category they're in for each person. So we have these two different data points for a given person. Their continuous variable, what their height or weight or whatever that is, cholesterol level, plus whatever category they're in. And here, with an independent samples t-test, by definition, we have two separate categories. Independent samples implies two samples. Therefore, when we are looking at the descriptive statistics, and I'm just going to pretend that we have a data set that only has 8 people in it, and 4 in each group, but this ... down here at the bottom really means that this continues on. Very rarely would we do something with a sample this small. So in terms of descriptive statistics, for each group, here we have group 1, we're going to make a histogram for group 1. We're also going to test the X bar for group 1. We are going to calculate a standard deviation for group 1, and it's always very handy to remind ourselves what our N was for that particular sample. Similarly, then we're going to make a histogram for group 2. These are the descriptive statistics, remember, that we're calculating for each one of these. And then here's our X bar, or our mean, for group 2, standard deviation for group 2, and also an N for group 2. Now, in the textbook, we have a real example of this, and this was an example that looked at plasma cholesterol, and we had a sample size in group 1 equal to 12 and a sample size in group 2 equal to 7. And the X bar for group 1 was 6.192. We'll take a look at this for our example down below. And the standard deviation for group 1 was 0.3919. mean for group 2 was 5.414, and standard deviation for group 2 was 0.6492. So find that example and you can follow along with what we're doing here. And I'd like to start doing something where I make a drawing of what this actually looks like. And so what I'm going to do is I'm going to be drawing something that kind of captures these two means, and I'll do that by saying here's group 1, here's group 2, whoops, here's group 2, and over here on the side is some kind of continuous variable that we're looking at. And if I was to graph this continuous variable, let's say this is our cholesterol variable, that's the example, and the x bar for sample number 1 is here, we probably have points along sort of a continuum, but the center of that group is right about here. Let's call this 6.192, and then the mean for group 2 maybe was closer to here, and that is 5.414, and it's also probably kind of spread out. These are the little data points for each person. You can see if you were to look at this from the side, and I'm going to draw this and then take it away, but you would see that this is probably kind of like a little normal curve that kind of gets superimposed on that dot diagram. So let's go ahead and take those two things back out. But that's sort of what you can imagine. Here we have our two different groups, group 1 and group 2. Now overall, if we were to draw something that's halfway in between them, this would be like our grand mean. And ultimately this is going to come in handy because a lot of times what we're wondering about is how far away are these group means from the grand mean. And that really is mathematically part of the underlying basis of the tests that we're going to be performing when we get down here closer to the bottom. So let's go ahead and take a look at this hypothesis from the textbook. A generic null and alternate hypotheses would be for a one sample t-test is mu1 is equal to mu2. Now if you think about it, another way of saying that, I'll put an or here because you don't have to write it both ways, but the difference between mu1 and mu2 is equal to 0 is really equivalent. These are two equivalent things. They are two different ways of saying the same thing, and you'll see when we talk about this 95% confidence interval how this difference, the version that we are looking at the difference, really makes a lot of sense there. So the alternate is mu1 is not equal to mu2, or that the difference is not equal to 0. So those are a couple of different ways of saying that. And in terms of the test, this is where we're going to say an independent t-test. Some people will call it an independent samples t-test, and that goes back to this whole idea that we took two independent samples from our population. And another name for it, and this is really important that you remember, is a student's t-test. Sometimes when you're taking multiple choice tests, they will say student's t-test, and this goes back to the gentleman William Seeley Gossett. Remember, he wrote under the pen name student. That was kind of his writing name, and so they named this after him, the student's t-test. The assumptions for a student's t-test are similar to what we've seen before. One of them is normality, and technically it's normality of the residuals. In other words, how far away each of these data points are from this grand mean. But there's another one, and so let's go back up here when I said we're measuring the means, both the means and the standard deviations. Now if we're looking at the means, it makes sense that we will have the assumption of normality, and a lot of the same rules apply with the central limit theorem and that sort of thing. But now all of a sudden you'll notice that we have two different standard deviations that we're dealing with. Over here with a paired or one sample, we did not have that issue because we were looking at a difference. the standard deviation difference and the x bar difference. And those were the foundational piece of our test. Now that we do have two standard deviations, we need to have what's called equal variance. And that becomes our second assumption. So now we not only have normality, but we also have equal variance. The test statistic that we are calculating looks a tiny bit different than what you've looked at before. And I'll write it here, and again we're doing a t statistic. So t equals x bar 1 minus x bar 2. So here's, remember how I said this, this difference would make more sense, and I'll put a line over it. X bar 1 over x bar 2, or sorry, minus x bar 2, divided by the standard error of x bar 1 minus x bar 2. Now remember how for the t statistic, this bottom number has a certain number of degrees of freedom, and this degrees of freedom helps us to adjust for the fact that the t statistic isn't exactly identical to the z statistic. So this degrees of freedom is equal to n1 minus 1 plus n2 minus 1. So in other words, our total sample size up here, minus 2. So I'll just say equals n total minus 2. So you'll notice that we're subtracting 2 out of the total. There is another way to make this adjustment with degrees of freedom, and this depends on whether this assumption of equal variances is met. Another one is called the degrees of freedom Welsh, and we'll be learning more about this too when we're looking at some future tests. And this is some kind of a complex adjustment. And your textbook also talks about another one, so or degrees of freedom conservative. And that is equal to the smaller of n1 minus 1 or n2 minus 1. In other words, whichever group is the smallest. And so that conservative degrees of freedom helps to adjust, again, this denominator data. Let's go back and think about our critical value. The critical value that we generally put in for this is whether it is less than or equal to 0.05. And then we actually take whatever test statistic that we compute and convert that into an actual calculated p-value. And let's see, do I have the calculated p-value written down, or do you have to look it up in the textbook? I think you have to probably look it up. So you can see what the p-value is that they come up with. So this is hypothesis testing. Remember, when we have a test statistic and convert it to a p-value, then there is the idea of estimation. And we can use either of these methods to think about testing a research question or the null hypothesis. So our 95% confidence interval is really a confidence interval for the difference between mu1 minus mu2. And so this is a difference. And this kind of goes back to this whole idea. Remember when we saw this mu1 minus mu2 is equal to 0? We're testing that particular mathematical version of our null hypothesis. And so the equation for that is the 95% confidence interval for the difference is equal to x bar 1 minus x bar 2, and we've seen that before, even right here, plus or minus whatever t statistic goes with that particular degrees of freedom, times the standard error of x bar 1 minus x bar 2. So in our particular example, when we look at, literally we take these numbers right here, we take 6.192 and 5.414 and we subtract them, and the number that we get here for x bar 1 minus x bar 2 is 0.778 plus or minus, and remember this 95% confidence interval depends on the degrees of freedom. If we have, in this particular case, I'll talk about this conservative, for degrees of freedom equals 6 because our smallest sample size, remember, was 7. And so degrees of freedom conservative equals 6. The corresponding t-value for that is equal to 2.447. So in place of this, we will put 2.447 times, and the standard error of x bar 1 minus x bar 2 is 0.20. Let's see if I can say this right. 0.2702. And so if we take this number and add 2.4 times 0.02, we would get 1.439. If we take 0.778 and subtract 2.4 times 0.02, we would get 0.117. So that's our 95% confidence interval for the difference. And the thing to notice specifically for this, remember, our null hypothesis is that that difference is equal to 0. This difference right here, this range between those two values, does not include the number 0. So we are 95% confident that the difference between those two values does not include 0. And so based on even just looking at the confidence interval, I know we'll also have a p-value that goes with this, and they always agree with each other. We would be able to say, no, I do not think that 0 is a reasonable number for that difference. Reject the null. It must be something else. mu1 must be something different than mu2. In other words, it's unlikely for these two samples with a sample difference of 0.778 to have been randomly drawn from target populations that have population differences equal to 0. So in the population, when we started out and we drew a sample from that, it would be pretty unlikely for us to draw these two samples if the underlying actual sample population means did not have that distribution. So here's the way we would put that. Again, this is sort of like an APA format, kind of a summary. On average, participants in group 1 had a significantly higher cholesterol. Here's our mean, standard error. Then participants in group 2, again mean and standard error. Here it says T. Here's degrees of freedom, and because this degrees of freedom is 17, I know that we actually did this more complicated mathematically standard error, and so that would be the 19 minus 2, and here's the value of the t, and here's our p-value equals 0.011. So that's how we would write it. This might be that the two groups were not significantly different. It could be that this would say had a lower cholesterol if we just wrote it in reverse. So this conclusion can be written all different kinds of ways, but those are the general parts that people are looking for in a specific way. Here's one of the very important takeaway messages. I'm going to put like massive stars next to it because it's such an important thing. Sample size for an independent samples t-test compared to, and here I'll scroll to the left, compared to the sample size calculation for a paired. So here's paired, here's independent. t-test. And the thing that I want you to notice, if I can kind of get them on the same screen together, the confidence is roughly exactly the same. Let me underline the parts that are identical. Here's your sigma squared, the z-value for the confidence, the power. Oops, that deserves a squared. So those are all exactly the same. The only thing that's added is that when you do an independent samples t-test, your sample size is multiplied, I need a different color, your sample size is multiplied by 2, and this is for each group. So for an independent samples t-test, we have 2 groups, so it's times 2 here, and it's times 2 here. So overall, the sample size is 4 times larger for an independent samples t-test that is running roughly the same kind of an analysis that a paired samples t-test is conducting. So all of the things are pretty much exactly the same. The same kind of dynamics happen as your difference goes up, your sample size goes up, or the difference goes down, sorry. Those kinds of things, those dynamics are identical, but the kind of question that you may get on a boards type scenario is, if you were to be able to repeat an independent samples t-test analysis, only you could now do it as paired, what would be the change that happens to the required sample size to achieve the same confidence and power? So what they're basically trying to find out is, do you know that kind of magic rule of times 4, which that a lot of times will be a deal breaker in terms of whether you can actually do a particular kind of a study. Is if you have to have 4 times as many people to analyze that, then it's going to take a lot more people to show that there's a difference. That's the value in having each person behaves as their own control. In other words, we take a baseline of them and we compare them to themselves. Remember when we did the whole thing with cornflakes and oat bran? When we had the same person eat both of those different diets, then all the rest of the things internally, whatever their physiology is, we can compare them to themselves. We don't have to have so much error because it's between different people. So that concludes our discussion on independent samples t-test. I hope that was helpful.